So this is basically what it looks like. On most days, this is kind of what happens to our magnetosphere. So you can see where solar wind comes in and it hits this front shield right here. This is called the shock bow, or the bow shock. And what happens then is that energy comes in and it gets diverted up and around the Earth. And when it does that, it kind of catches these magnetic fields that are down here and drags them way out beyond the Earth. Again, in front, those magnetic fields get compressed inward. So we get compression in the front, elongation in the back, and notice right here, okay, that's that shadow that we talked about before. So the magnetic fields basically act like channels that flow the sun's energy out and away from Earth. Again, the whole role of the magnetosphere is to deflect the energy from the sun. And that's basically what it does. It deflects a lot of the harmful energy emitted by the sun and sends it out and around the Earth. But now we get to answer the question, so then how do we get the auroras? How does the magnetosphere play a role in how we get the auroras? Well, the magnetosphere does a really great job at deflecting the sun's energy, but it can't deflect everything, right? So, Tanner, you played football, right? Offense? Yeah, okay. So, main goal of offense is to keep the defense from crossing the line, right? You guys do pretty much a good job of that, right? But you can't block them all, can you? All right? Same thing here with the magnetosphere. The magnetosphere is going to do a great job of blocking most of the things coming in, but it can't deflect them all. And so there's the small amount of particles that are able to get into Earth's atmosphere, and you can see right here. Remember when we talked about the fact that the poles, the magnetic fields are parallel and they're vertical? So what happens, think about it like this. I'm coming in as this wave of charged particles, and I hit the front edge here. Think about how that's acting. Perpendicular to my direction, right? So therefore, it's going to deflect me around. But if my charged particle is coming in this direction, now what have I done between my fields? Now I'm running parallel to my fields, and I can go right in. So what happens there is in these polar regions, that's why our auroras take place in the poles. That's why it's the weakest region of the magnetosphere. It's because these magnetic fields are parallel, it allows a direct route to Earth's atmosphere. And that's really important. We're starting to understand the basis now about the auroras. The fact that we're able to go in directly at the poles and make contact with Earth's atmosphere. And the main reason why we're able to do that is because those magnetic fields are parallel. So what happens then? So we have this solar energy coming in and making contact with Earth's atmosphere. But what's hanging out in our upper atmosphere? Just think about it for a minute. What is up there? In our very high upper atmosphere, what's hanging out up there? Okay, give me a hint. It's more charged particles. What happens when two charged particles collide? Got a lot of energy, right? Okay. So here's how the auroras are created. You might want to get ready to write. I'm going to walk you through this. So what happens is the charged particles come in from the sun. Most of them get deflected away due to the magnetosphere. A few of them are able to enter at the poles because our magnetic fields are parallel, right? And there's a big gap. We call that the polar cusp. And we talked about that right before we went to lunch. What happens there is those charged particles follow along in between those fields and it makes contact with our upper atmosphere. When it makes contact, it releases that energy in the form of light, because what's happening is those electrons are getting excited. There's a lot of energy coming in, so the little electrons start to get really vibrating away, and they get super excited. And just like watching a little kid that gets really excited, can't really contain themselves, their eyes all lit up. The same thing happens with those upper atmospheric ions. They get so energized that their electrons literally jump in energy level. And when they do that, it emits that energy in the form of light. And that's what we see. So again, this is the thing to me that I find to be the most amazing part about the auroras, that what we're seeing on this scale, when we're really looking at this on a global level, that is literally taking place on an atomic level. But it's happening on such a grand scale, we see it as this ribbon of light in our upper atmosphere. But it's literally happening one atom at a time. So when you start putting that in perspective, and I hope that it helps you guys to appreciate what you're really seeing when you see these pictures. This is really a chemical reaction taking place. It's taking place at a very small scale, but yet we see it on a grand scale. It's kind of like weather. It starts as a very minute scale, we do get to see it then again as a very large scale. Okay. All right, before I move on, any questions on how the auroras are formed? Solar wind comes into the upper poles, energy gets the upper atmosphere ions super excited, the electrons jump in energy level, and then we have light being emitted. Glad you guys don't have any questions on that. We'll see about that Friday.